Hello, students. It is my pleasure to take you through this revision. So we're going to solve some questions based on, we're going to solve some questions just to prepare you for your upcoming examinations. So this is the first one I'll be solving. A child's toy launches a model parachutist of mass 0.4 kilogram vertically upwards. The model parachutist reaches a maximum height of 8.4 meters. Calculate the gravitational potential energy gained by the parachutist, by the model parachutist. What is the formula for gravitational potential energy? Gravitational potential energy is equal to mass multiplied by gravitational field strength multiplied by the height. What is the mass of the model parachutist? 0.4 kilogram. So you write 0.4 multiplied by gravitational field strength. We always take it as 10 meters per second square for your IGCSE level. Then the height has been given to us as 8.5 meters. So you write 8.5 here. Then you multiply all of this. This gives you 34 joules. So you write your answer here. The gravitational potential energy is 34 joules. Now we proceed. Next question. You are to calculate the minimum possible speed with which the model parachutist was launched. How do you get the minimum possible speed with which the model parachutist was launched? Now, according to the question, we have a model parachutist and was launched upwards. Okay, it was thrown upwards and the model parachutist attained a height of 8.5 meters. Take note that in order to launch this parachutist upwards, you have to throw it upwards, giving it a kinetic energy. Yes, so you give it a kinetic energy in order to enable it to move upwards. So when it goes upwards and attains the maximum height, at that point, it then possesses a gravitational potential energy. You know, in the first question we saw, what we calculated was the gravitational potential energy. Now, with what kinetic energy would you throw it in order to give you this gravitational potential energy? So according to the law of conservation of energy, that energy can be converted from one form to another. So the kinetic energy given to the model parachutist was converted to gravitational potential energy when it rises upwards. So you just state it here that your kinetic energy given to the model parachutist was converted to gravitational potential energy. So here we assume no energy was lost during this process. So you state the formula. We don't need this. All of these are not part of your calculation, okay? So I just stated all of these here in order to ensure the concept is clear. So this is the law we are applying, the law of conservation of energy. What's the formula for kinetic energy? Have the formula for kinetic energy is half mv squared, where m is the mass and v is the speed, or you call it the velocity. Half mv squared equal to the gravitational potential energy is mgh. Now you can see that m is common on both sides. So what can you do here? You can remove it from the expression. Yes, so we can cancel out m from both sides of this equation. So let me cancel out m from both sides. So the equation then reduces to what? The equation reduces to half v squared is equal to gh. Now let's see, if half v squared is equal to gh, then we substitute. Half is the same thing as saying 0.5. Half is 0.5. So we have 0.5 v squared is equal to g. You know, g is always 10. And what's the height? The height at which you threw the model parachutist was 8.5 meters. 8.5 meters. All of this value were picked from the original question. And this is the original question. You are given the mass of the model parachutist and you are given the height to which it was thrown. G was not given to you because when solving questions on this topic with the assumption that all of this happen on the planet Earth, we always take the value of the gravitational constant, the gravitational field constant G, we always take its value to be 10 meters per second squared. So that is what we use. That's what we've used here. So in order to get the value of v squared, you divide both sides by 0.5 so that v squared can stand alone. Divide both sides by 0.5. Now, when 0.5 cancels out this 0.5, you have v squared. This doesn't look good. So you have v squared equal to, now you take your calculator and you multiply. 10 multiplied by 8.5, you get 85. 85 divided by 0.5, you will get 170. Now, if v squared is equal to 170, how will you get the value of v? You take the square root of both sides. Take the square root of the expression on the left-hand side. This doesn't look good. So you take the square root of the expression on the left-hand side, and you also take the square root of the expression on the right-hand side. Take the square root of v squared, and you take the square root of 170. So square root of v squared will give you v, and square root of 170 will give you 13.038, or you can approximate it to 13.04 meters per second. So that is the speed. So you write your speed as 13.04 meters per second. The third question then says, in practice, in a real-life setting, in practice, the launch speed must be greater than the value calculated in question AII. Explain why. Do you remember very well that when I wanted to solve this question, I talked about the model parachutist being launched upwards, and then it attained a maximum height of 8.5 meters. 8.5 meters is the maximum height. How do you make this model parachutist attain this height? You throw it up, but you give it a kinetic energy. And as it goes upwards, all of that kinetic energy will be converted to gravitational potential energy. But you notice that in the real life setting, all of that kinetic energy would not be converted to gravitational potential energy. Some energy will be lost along the line. Some energy will be lost due to what? Due to drag. Yes, when we talk of drag, we are talking about air resistance. And if we were to draw the energy diagram for this situation, this is what the energy diagram would look like. The Sankey diagram should look like this. So this represents the kinetic energy in the beginning. So you know you gave these model parachutes some kinetic energy, and then the kinetic energy made it go upwards. And at the topmost point, it possesses some gravitational potential energy. So at the end, you have gravitational potential energy. But take note that some energy will be lost along the line. And this represents the energy loss along the line. Energy will be lost due to drag, okay? Or you call it air resistance. Air resistance consumes some energy, and that's the main reason why you have to give this model parachutists more kinetic energy than the gravitational potential energy you are expecting. So you must launch it with a speed that is higher than 13.04. Otherwise, if you launch it with 13.04, at the end, it will not give you the gravitational potential energy, because gravitational potential energy is not equal to kinetic energy. So if you give it a speed that ensures that the kinetic energy is 170 joules, at the end, by the time you subtract losses from the kinetic energy with which you are launching this model parachutist, at the end, you won't get 170 joules. Yes, so if you give it a kinetic energy of 170 joules and 10 joules is consumed by drag, at the end of the day, you get 160 joules. Yeah, so if 10 joules will be consumed by drag, you launch it with 180 joules. So when drag consumes 10 joules, you get 170 joules at the end. So in practice, the launch speed must be greater than the value calculated in AII. Explain why. And what explanation will you give for that? You will ask to explain why, in practice, the launch speed will be greater than the value calculated there. What explanation will you give to that? This is the explanation. Drag consumes some energy. Drag consumes some energy. Yeah. Or you say drag consumes part of the kinetic energy with which you've launched it. Okay. I think that one is good enough. Drag consumes some. Let me state it this way. Drag consumes some of the kinetic energy. Some of the kinetic energy with which you launch the model parachutist. Hence, you must launch it with a speed greater than the calculated value in order to accommodate for losses, or in order to account for losses. That is the explanation. So this brings us to the end of this question, and that is exactly what your IGCSE question would look like. It won't be exactly the same question, of course, not the same question, but your questions will come in this manner. Let's take another question. An electric train is initially at rest at a railway station. The motor causes a constant pulse of 3,600 Newton to act on the train, and the train begins to move. State the form of energy gained by the train as it begins to move. You know, you've been told here that the motor causes a constant force of 360 Newton to act on the train, and the train begins to move. State the form of energy gained by the train as it begins to move. Energy gained by objects in motion. What form of energy is that? Is it chemical energy, thermal energy, gravitational potential energy, or kinetic energy? We all know very well that it is kinetic energy, since it has been stated here that the object is in motion. So that form of energy is kinetic energy. So you just write kinetic energy here, and you get your full mark. So let's proceed. The train travels a distance of 400 kilometers along a straight horizontal track. Calculate the work done on the train during this part of the journey. What's the formula you use to calculate the work done? Work done is equal to force multiplied by the distance moved by the force. Now, let us assume that this is the train. You know, the train is being powered by some motors as stated in the question. Now, the motor produced a force of 360,000 newtons. Now we've been given the distance moved by that force, and you have to calculate the work done. What's the formula for calculating work done? Work done is equal to force multiplied by distance. But take note that the SI unit of distance here is kilometers. So you have to convert from kilometers to meter. Okay, let us substitute. The force is 360,000 Newton as stated in question A. The A part of this question states is that the force is 360,000 Newton. You know, we are given the force here. The force is 360,000 Newton. So we are using this force, and we multiply this force by the distance given to us. So let me go back to it. So we multiply 360,000 we multiply 360,000 so you multiply it by what? You multiply by the distance. And what's the distance? 4 kilometers. We don't use kilometer as the SI unit of distance in physics. The SI unit of distance is meter. So you have to convert from kilometers to meter. How do you convert? You multiply that 4 by 1,000. That gives you 4,000 meters. That's the distance. Now multiply 360,000 by 4,000. That gives you 1,400,000,000. So from this, you see that the work done in joules is 1,440,000,000. 1,440,000,000 joules. So, you know, normally you have to state the SI unit, but since the SI unit is stated here, then it is not necessary you state the SI unit again. This is not part of a solution. This is just an explanation for you to easily understand what the question requires of us. Now let's take the last part of the question. Calculate the mass, the mass of the train is 450,000 kilograms. Calculate the maximum possible speed of the train at the end of the first 4 kilometers of the journey. What is the relationship between the mass and the maximum possible speed of the train? Now, let us assume that this is the track and this is the train in question. Let's assume that this is the train. Okay, so this is the track, this is the train. Now, this train is going to move and cover a distance of 4 kilometers. 4 kilometers, or you express it as 4,000 meters, since 1 kilometer is 1,000 meters. Now, that's the distance the train is expected to cover. what is the force that's applied by this motor? You know, this motor attached to this shaft here. These motors, each of these will produce, all of the motors rather, would produce a force of 360,000 Newton, as stated in the early part of the question. We have the force as 360,000 Newton, and we have the distance as 4,000 meters or 4 kilometers. Now you'll be given the mass of the train. Take note that the work done by this motor in pushing this train, that work is used in giving this train some kinetic energy, because the train is moving along a straight path. So the work done by the motor would give this train some kinetic energy. So the work done, which you have calculated, must be equal to the kinetic energy given to the train, with the assumption that no form of energy is lost. What's the formula for work done? Force times distance, which we have calculated in the early part of this question. Okay, so we have force times distance is equal to kinetic energy. Force multiplied by the distance moved in the direction of the force, which is 4 kilometers distance, must be equal to kinetic energy, which is half mv squared. You know, this is also in line with the law of conservation of energy. Now let us substitute. What is the force? 360,000. 360,000 multiplied by the distance. The distance is 4 kilometers, which is 4,000. You know, we've done this already, but let's just continue with it. Must be equal to half mv squared. Half multiplied by our mass. Our mass is 450,000. 450,000 multiplied by the velocity squared. What is the velocity? You have to calculate the maximum possible speed. So speed in this context also refers to the velocity. Yeah. So you know we are not putting the direction into consideration. So half multiplied by mv squared. This v squared is what we are looking for right now. So let me remove all of these illustration. All of these illustrations are just meant for you to easily understand what the question requires of us. So they are not part of your solution. Okay, so physics is easier to solve when you are able to visualize what the problem is. See, so after visualizing, then you'll be able to derive the appropriate formula you use to solve the problem. 260,000 multiplied by 4,000, that will give you 144,000, just as we have calculated before. So you get 144, sorry, you get 1,440,000. You get 1,440,000. 1,440,000. Sorry, 1,440,000,000 rather. Pardon my mistake. 1,440,000,000 must be equal to half of 450,000. That will give you 225,000. So that gives you 225,000 v squared. Now you can see we want VCS to stand alone. So what will you do? You can divide both sides by the coefficient of v squared. So if you decide to divide both sides by 225,000, divide this one by 225,000. You also divide the expression on the left-hand side by 225,000. What will you have? By the time you cancel out, by the time you cancel out, 225,000 will cancel out 225,000. Right? Good. So you have v squared left. So you have v squared is equal to what? V squared is equal to, divide this two, you will get 6,400. So if v squared is equal to 6,400, how you get the value of v? You take the square root of both sides of this expression. You take the square root of v squared, you also take the square root of 6,400. The square root of v squared will give you v, and the square root of 6,400 will give you 80. So your answer is 80 meters per second. In practice, the speed of the train is much less than the value calculated in II. So just one reason why this is true. Why would the speed of the train be lesser than what is calculated? You know, this calculation assumes that the work done by the motor on the train must, all of that work done by the motor will be converted to kinetic energy. But in practice, all of the work done will not be converted to kinetic energy because some energy will be lost due to friction. Friction will consume some energy. So just one reason, your reason is because friction will consume some energy. You know, friction opposes motion. So friction would consume some energy. Friction would consume some energy. Friction would consume some energy. And that's it. Yes, so friction opposes motion. The frictional force between the tires of the train and the railway line would cause some energy to be wasted during the motion. So this is all we can take right now. We'll continue the class some other time. Thank you for watching. Do have a nice day.